It turns out boring is actually quite interesting. Look, we're all required to make that joke, okay? It's mandated by the Machinists Guild of Greater North Canada, but I promise I will not do it again in this video. Hello Internet, my name is Quinn and this is Blondihacks. This is Lathe Skills, a series of quick videos on getting started in machining. This is episode 22, Boring. Oh, it's so hard not to make that joke every time. Fundamentally, boring is a single point way of making a hole. And the reason that matters is for all the reasons that all single point operations matter, which is precision. A single point tool means the geometry of the surface is dictated only by the slides on the machine and nothing about the tool itself. Take, for example, the classic precision multi-point hole cutting tool, the reamer. All it takes is one of these flutes to be a little dull or a little bit off on the grind, and it's going to be cutting heavier on one side than the other as this tool spins, and now your hole is going to be a little oversized or a little eccentric or whatnot. Furthermore, all multi-point cutting tools follow whatever pilot hole is there, so you're never going to be able to guarantee positional accuracy with a reamed hole because your drill pilot is never going to be perfectly positionally accurate. Whereas single-point tools like a boring bar can move an existing surface regardless of the initial shape and position of that surface. And then of course boring is also useful for making holes that are larger than your largest multi-point cutting tools. Boring bars come in a lot of different types, but here's some common ones that you'll see nowadays. The three most obvious ones are the insert variety, and these are probably mostly what you'll find nowadays. So you'll have a steel bar with a carbide insert in the end, and then the insert has all the right clearances on it that you need for boring. Before the advent of insert tooling, you would have more typically seen a boring bar like this. This is just a single solid piece of high-speed steel that's been ground into a boring bar shape with all the appropriate clearances. This is actually part of the Grizzly pre-ground set that I link to below, and this is a perfectly fine boring bar for use today, so you can start with this. Both of these are carbide insert, which is very common, but not the only choice. This here is a high-speed steel insert boring bar. This is an Arthur Warner Company boring bar. Hashtag not sponsored, but this is actually my favorite small boring bar, especially for brass because the insert has no top rake on it, which is perfect for brass. In the olden days, boring bars were frequently made as a solid steel bar with a cross hole in it and then a small piece of high-speed steel pushed through that hole and then the appropriate clearances ground on that. So it would look something like this. Now this is actually a quick and dirty fly cutter that I made for a project, but it's the same idea. The body of the fly cutter is steel and then there's a little piece of high-speed steel that's been secured in a hole and all the correct clearances ground on that. There's a lot more than meets the eye to the shanks on boring bars. These two boring bars look superficially the same. You figure, well, this one must be stronger because it's much, much thicker, but this boring bar is mild steel, and this one is solid carbide. And despite being much smaller, this one is vastly, vastly more rigid than the cheaper, bigger one. A carbide shank on a boring bar is a huge advantage because, rigidity is always important in machining, but with boring, it's even more so than usual. You're going to encounter all sorts of chatter problems that you never would with other operations because with a boring bar, you're always hanging way out in the wind, as it were. You'll also encounter different shank designs. These boring bars are both right side up, but notice that while they both have a flat top, this one has a round bottom and this one has a flat bottom. Those little subtleties are important because when it comes time to put the boring bar on your lathe, you need to put it in a tool holder just like anything else. And the tool holder you choose needs to be a match for the boring bar. So if the boring bar has a flat bottom on it, then you want to put it in a flat bottomed tool holder, of course. And if it's got a round bottom, then you want to put it in a V-groove tool holder. Some boring bars are completely round, in which case you probably want to use this style of boring bar holder, which is more typically seen with larger boring bars, but you can see how it's a completely different clamping arrangement than a traditional quick change tool post holder, and it's designed for holding something completely round in a secure way. Now, if the top of the boring bar is flat, then that means the orientation of the bar is going to be fixed. It's going to be set by the set screws on the tool holder clamping down on that. The bar can't rotate to different positions. And that's usually what you want for smaller boring bars like this. However, it is also sometimes nice to be able to change the angle of the boring bar because that allows you to control the rake of the tool. And just like with a turning tool, the top rake needs to match the material that you're cutting. So 0 top rake for brass, or positive rake for steel, or a lot of positive rake for aluminum, and so on. There's one weird exception unique to boring bars though for top rake. You can see that this bar is sitting horizontal in the correct position, but the tool actually has a negative rake on it. So why would you ever want that? Negative rake tooling creates higher tool pressure. Not ideal for a boring bar, you would think, but the reason that they're doing that is to provide clearance under the insert. Here's how that works. If this tool was flat, let's say I'm inside this bore here, you can see that if I try to get that tool on center where it needs to be, I'm interfering with the bottom of the bore there. However, if I angle this tool like so, I get more clearance underneath it. So you can actually get into smaller bores. And sometimes they also do this because it allows you to flip the insert over and use more corners if the insert does not have bottom clearance built into it. And compare that to this smaller boring bar that has neutral rake. In our same bore here, it has clearance, but the way that they do that is by having the insert stick out further past the boring bar. But this is going to be less rigid and not as capable of heavy cuts as the big negative rake bar is. And this really is the central challenge of boring bar design. Normal turning tools live out here where there's all kinds of space. They can be as big as they need to be, as rigid as they need to be. Boring bars live their whole lives in these tiny little spaces, and usually with lots and lots of stick out because you're trying to go deep on things. So they have a much, much higher challenge when it comes to rigidity. It's a perfect storm of needing to be small, needing to have long reach, and needing to make cuts inside of a part. Let's start with the simplest boring operation, and that's a through bore. You would do this when you need a hole that's extremely accurate and something like a reamer isn't even going to be good enough. Now, reamers are good enough for 99% of small holes that need to be accurate, but boring is technically slightly more accurate. So for those times when it really, really matters, if you need an absolutely perfect fit, boring is the way to go. What's interesting about boring compared to other operations though is you have to start by making room for the boring bar. We can't even get in there. You can't just push a boring bar into the stock like you can with other cutting tools. So we have to start by drilling a hole. Now you don't have to center drill or pilot drill or do anything like that because any eccentricity or out of roundness in that hole is going to be fixed by the boring bar because again it's a single point cutting tool, so it can do that. So the drilling is just to make physical clearance for the tool and nothing else. So I'm using a small drill here because I have a small lathe, but you can just push through whatever the largest drill is that your lathe can handle to get enough clearance for the boring bar. Next, we need to square up the tool post, not because it's going to affect the cut, because remember this is a single point cutting tool, angle of the tool post doesn't matter, but if the boring bar isn't straight, then the deeper it gets into the hole, the more you're going to lose clearance on the back side of the bar. Now, sometimes that's an advantage. There are certain geometries where angling the tool post one way or the other actually helps you get the boring bar into a tricky spot, but most of the time you're just going to want it to be square. And then typically you're going to put the boring bar on the back of the tool post over here. As with any lathe operation, the tool has to be on center, so if this is your first time using this particular boring bar, make sure to flip it around, line it up with your tailstock center, and make sure that the top surface of this tool, which is doing the cutting, is exactly on the vertical center line of your lathe. Otherwise, this is just like any other turning operation. For a through bore like this, we're not worried about precision depth, so all you need to do is touch off on the inside surface there. Come back out clear of the work, just like you would with turning on the outside, and now you can zero that if you like, and then dial in your depth of cut. And of course, because we're cutting on the inside surface, the depth of cut is reversed from what you expect, so you pull the cross slide out to set depth of cut. Feeds and speeds are technically the same as turning, but be aware you may want to take lighter cuts and go easier with a boring bar because, again, you're always going to have much less rigidity with a boring bar than any other kind of lathe tool. You can power feed, of course, just like any other tool, but definitely be thinking about where that boring bar is going to end up when it gets inside. If you're doing a larger bore, there's a good chance you may hit the back of the chuck or a chuck jaw or some other feature in your spindle. In this case, I'm boring a small hole, so I've got plenty of notice when it gets through that bore. Always plan your end game ahead of time with a boring bar. You want to make sure that when that cutting tool pokes through the back that it's not going to hit anything, and you want to make sure you're going to have enough extension on that boring bar to get as deep as you need to go. And of course, make sure that the tool post isn't going to hit the work, but you also always want this boring bar retracted as much as you possibly can to, again, claw back any amount of rigidity that you can, which is just always at a super premium with boring. An easy illustration of the rigidity challenges with boring is to simply pull this cutter back out without adjusting anything on the depth of cut. Just like you would with turning, after each pass, you're going to wind it back and set in a new depth. Well, watch what happens with boring. There's a fine spiral scratch in there, and this was a light cut in an easy material, but there's still a fine spiral scratch in there. And what that means is that on the way back, the boring bar sprung back a little bit from where it was when it made the first pass inward, and it scratched up the surface. If the boring bar had not deflected during the cut, then on the return trip it would be exactly on that surface and wouldn't be cutting it. So with boring bars, you always are going to need to do a spring pass, or if your final pass is right on dimension, make sure to wind the boring bar clear of the work before pulling it out so you don't scratch up the surface. Typically when I'm really trying to nail a dimension, I will feed in and feed back out again before measuring on every single pass, because then I know that I've taken all the spring out of the boring bar and the surface that it's cutting is going to be where the hand wheel thinks that surface is. The next level on boring challenge is boring to an inside shoulder. So for that, you need to make sure you have the right clearances on the end of your boring bar. If you're grinding your own, for example, commercial boring bars may look like they have a flat end, but in fact, they're always going to have at least a 10-degree backward clearance on the end of that tool. And that's so that you can go into a bore and feed outward and face the back of an inside shoulder. Let's see what that looks like. To bore to a precisely depthed shoulder, now we do care about the depth of the tool in the work, so now we need to touch off on the face and on the inside shoulder. The same touch-off methods you would use for any other tool apply here. You can do it with the lathe running and look for a very fine chip to appear. You can use a feeler gauge or any other method. I'm just going to lightly touch off by hand with the machine stationary so you can hear what I'm saying. So I like to touch off on the inside surface first, and you'll see why here in a second. So I'm just going to feed out on the cross slide until I feel that tool touch, and then I'm going to bring it out. And then I'm going to zero my cross slide hand wheel right there so that my depth of cut will be correct. And then I'm going to feed out towards the face, and then I'm going to bring it in and touch it off lightly on the face. And then I'm going to set an indicator on my carriage to measure my travel on the depth. Now, if you have a DRO, of course, you can just zero your DRO at this point, but I'm going to set an indicator. And now I can feed back in towards the bore. I need to overshoot and come back to take the backlash out of my cross slide, because remember I set the zero when I was feeding that way, so I need to be feeding that way again to get back to my zero. That's zero there, so I know that cutter is now exactly on this corner there. It's just on this surface and just on the inside surface, and so now I can bring it a little clear of the face. I can dial in my depth of cut, feeding that way, of course, and now I can feed in until I get to the depth reading that I want on the indicator. So my technique for this is the same as turning to a shoulder on the outside of a part. Go watch my video on turning to a shoulder for that, but basically I feed inwards to a few thousandths short of my final desired shoulder depth on each pass, and then on the final pass I feed all the way into zero on the indicator, lock the carriage, and then feed across to face the back of the shoulder. So with that simple method, we know that this larger bore is going to be the correct diameter, the smaller bore is correct because we made it earlier, and then I know that this shoulder depth is correct, and by extension this shoulder width is correct. So that's an easy way to hit all the dimensions that you need with nothing more than an indicator and a little basic technique. Now on to the trickiest operation, a blind hole bore. Now the best thing to do for a blind hole is don't do them. If you're designing parts, just design them so that a drill cone in the bottom of your hole is acceptable, or make things through holes where you can. But if you're making a part that absolutely needs a perfectly flat-bottomed blind hole, well, there is a way to do it with the boring bar. As before, we have to start by drilling to get clearance for the boring bar, but this is now much trickier because what you need to do is get the tip of the drill cone for each of your drills to land at the bottom of your hole, or preferably just a little bit shy, like 5 or 10 thousandths shy of where you need the bottom of that blind hole to be. So you better be good at precision drilling depths on your tailstock to do this. One straightforward way is to put a toolmaker's clamp on your quill and then preload an indicator all the way up for the depth that you want. Then use a feeler gauge to set the end of the drill exactly on the end of the work. Add that feeler gauge to your depth, and then use that to measure the travel of the drill. And of course, it's pulling away from the indicator, so you're moving in the negative there on the indicator. I'm making this blind hole shallow so you can see what I'm doing, but normally they're going to be deep and you're doing all of this stuff blind, so keep that in mind. But you can see that we have two exciting new problems. First is this drill cone that we have to deal with. You might think, well, I can just bore that right out of there, but because that's a cone, the deeper in we get, the deeper your depth of cut is getting. So if I start my cutter out here and just try to push straight in, you're going to get into that drill cone, and very soon you're going to be cleaning the toilets in Chattertown. You don't even want to be the mayor of Chattertown. The whole place is just awful, trust me. The second fun problem is that we need a lot more clearance than we did before. This amount of clearance here is enough for a through bore, but in order to face the entire back of a blind hole, you need twice as much clearance because the boring bar has to be able to feed all the way across to the center line without hitting the back of the hole. So for a given size hole, you need a much smaller boring bar in order to face the entire back of it. That limitation is often a deal breaker because you need a super small boring bar, or the hole is too deep, and so the boring bar fully extended doesn't have enough rigidity to face the back of the hole, and so on. So this is another reason why you really want to avoid flat-bottomed blind holes in your design if you can help it. So for the purposes of this demonstration, I'm going to assume that the final hole diameter that I need is larger than this, and so I'm going to get in here and face the sides of this out a little bit larger to get the clearance that I'm going to need to face across the back of the hole, because I don't have a boring bar small enough to do a 1/2 inch hole like this. Okay, so now my hole is such that this boring bar will be able to face all the way across the back without hitting the back of that hole, barely. The cutting point on the tool can reach the center line of the part. Now we need to deal with that drill cone in the bottom, and basically what we have to do is rough this in and then bring it to final shape and size with finishing passes, just like you would with any other part, except we're kind of inverted now because we're working inside. So I typically start in the center and feed out into the taper of the drill cone, and then you can control your depth of cut quite easily. I was feeding in at the center, 30 thou depth of cut at a time, and then feeding out until I was 10 thou short of my final hole dimension, and then I've stopped 30 or 40 thou short of the final depth, and you can still see the remainder of the center of the drill cone there. Now, tracking those depths and surfaces is fairly easy to do on a shallow blind hole like this because you can see the cutter. If you're deep in a hole, then you're effectively flying on instruments, if you like, and you really got to have indicators set up on your carriage and your cross slide to keep track of where the final position of this surface and the back surface are, so that as you're facing out that drill cone, you can stop 10 thou short of each dimension and then come back in and do your final pass. And this final pass works just like turning to a shoulder. I go to my final hole diameter, 1/10 thou depth of cut or less preferably, feed all the way into my final depth, lock the carriage, feed all the way across to the center to face the back, and we're done. You can also do that the other way if you prefer. You can start in the center at the final depth, face out to the final diameter, and then pull the cutter back. People prefer doing it different ways, but it's up to you. And there we go. This is going to be an on dimension and on depth flat bottomed hole, all made possible by the boring bar. Now, don't underestimate the challenge of a feature like this, so for your first couple of tries at it, you definitely want to do a shallow one where you can see what the boring bar is doing and you don't have to worry about losing track of where you are on the hand wheels. And obviously a DRO makes all this much easier, but if you need to do a deep blind one, then make sure to set up 2 indicators, one on your carriage and one on your cross slide, so you can keep track of both these surfaces, because once again you're flying completely on instruments at that point. The trickiest part of that procedure is getting rid of that drill cone and ending up at the correct depth on the back face, primarily because you really can't plunge with boring bars more than a few thousandths, so you really need the bottom of that drill cone to stop just short of your final face depth that you need down there. Now, if you can live with a little bit of a drill cone in the center, which usually you can, then that's not so critical. But there are some tricks to make flattening that hole a little bit easier before you go in with the boring bar. One is to go in with a 2-flute center cutting end mill. Get yourself an end mill holder. I don't recommend chucking end mills directly in Jacob's chucks. They don't hold very well, and it's not really good for the Jacob's chuck. So put it in an end mill holder in your tailstock, and you can plunge straight into your drill cone and flatten out the majority of it. Now, contrary to amateur belief, end mills don't actually make flat-bottomed holes. They actually leave a slight positive cone when they're done, because there's a clearance angle leading into the center on both flutes at the bottom. So you're going to end up with the outsides of the hole of your so-called flat spot being a little deeper than the center. So keep that in mind if you're trying to hit an exact depth. But again, that positive cone is easily removed with the boring bar on your finishing pass. Another option is to grind a flat bottom drill. Now, this is actually a commercial DeWalt drill that comes with a flat grind. They call it their pilot point. And so this also works quite well, as long as you can, again, live with that little bit of a point left in the bottom of your hole, or you can take a regular drill and just grind a flat grind on it. So there's 2 options to make flattening out the drill cone a little bit less stressful. I hope this little video helps you understand the physics and the use cases for boring on the lathe, and I hope you'll give it a try. It's kind of an intermediate level lathe skill that every home shop machinist is going to need to master sooner or later. So give these techniques a try, and thank you very much for watching. If you like these videos and you can swing it, throw me a little love there on Patreon. That's really what keeps this channel going. And I will see you next time.